In this video, we'll talk about weight initialization techniques in PyTorch. Weight initialization is defining the parameters for a neural network before the training actually begins. So the focus of this video will be providing an overview of different weight initialization techniques in PyTorch. The notebook used for this video will be available on GitHub and I will provide the link in the description box. So let's begin. First, we import all the relevant libraries for building this model. We get the training data in a CSV format, do some pre-processing which includes min-max normalization, and then splitting the data into training and validation data. Let's start by looking at how weights are initialized by default in PyTorch. First, we'll define the model structure. If you have watched my previous video, you will find this slightly different because this time I am defining this using a model class. The model class that I define has two functions, a init function and a forward propagation function. In the init function, we define what the model structure will be. In this case, there is a simple neural network with two layers, an input layer and an output layer. ReLU is the activation function for the input layer and sigmoid is the activation function for the output layer. The function named forward defines how do we do forward propagation through this neural network and returns the output value from that neural network after doing a forward propagation. We also define a function to train the model. This function is the same function that we have seen in my previous videos on how to create simple neural networks, so you can go and refer back to those videos. Finally, we define a function to print the ROC AUC value on the validation dataset. Now let's use whatever we have created till now to define a model, train the model and print the ROC AUC value. We define an object of this model class, call the train model function to train our neural network and then print the AUC value on our validation dataset. As you can see, the model has been trained for 15 epochs. We are printing the training loss and validation loss after each epoch. And finally, we are printing the AUC value, which in this case is 0.859. Now let's see one more initialization technique, which is zero initialization. Zero initialization is simply setting all the weights to zero. While this is a very simple weight initialization technique, this is generally not used because the model is not able to learn any meaningful patterns here. One variant of zero initialization might be where you set all the weights, essentially all the parameters to the same non-zero value, but that technique is also not commonly used because the model is not able to learn any meaningful patterns from the training data. I have provided some links to PyTorch documentation all throughout this notebook which talks about different weight initialization techniques. You can refer to these links and learn more about various weight initialization techniques and functions in PyTorch. Coming back to the notebook, let's see how zero initialization was done in this case. I have added two lines of code after the first linear layer is defined. These two lines of code will initialize the weights and biases to zero. We do the same thing after the second layer as well, where we define weights and biases to zero. The rest of the class remains same. So what we can now do is we can define an object of model 0 class and print the initial values of parameters for this model. You can see that all weights and biases are set to 0 here. We train the model and then print the AUC value. You can see that the model has not actually learned from training data because the AUC value is 0.5. Also, you can see that the weights and biases remain 0 even after training. The values that you see below are essentially the weight and biases value after the model has been trained. Now, zero initialization is not very useful, so let's look at one weight initialization technique which is actually useful for training neural networks, which is random initialization. Random initialization is setting weights randomly from a uniform or a normal distribution. So there are two variants to random initialization. We can either use a uniform distribution or a normal distribution. It's commonly used to break symmetry and the weights are drawn from a distribution with mean set to 0 and a small variance. Similar to what we had done earlier, we write these two lines here after the first linear layer to initialize the weights and biases for the first layer. We use a normal distribution, set the mean to 0 and standard deviation to 0.01. We do the same thing after the second layer, setting mean to 0 and standard deviation to 0.01. We follow the same technique where we define an object of the model normal class and then print the initial parameter values. which you can see here. We then train the model and print the AOC value. In this case, you can see that the model has actually learned something because the AOC value is 0.859, which is much better than the 0.5 AOC value that we saw earlier. And you can also compare the value of parameters which are different after training. Let's look at one more weight initialization technique, which is called Xavier initialization. This initialization technique is designed to work well with activation functions like tanh and sigmoid. Weights are initialized by drawing from a distribution with mean 0 and variance of 1 by number of input units that we have in our neural network. Let's look at how the class is defined. After defining a linear layer, we use Xavier normal weight initialization, where we specify a gain parameter of 0.01. This has been done only for the weight parameters of this neural network. I continue to use normal distribution for initializing the biases for our model. And I repeat the same thing for the second layer for my neural network. Next, we create an object of model class. We print the parameter value before training. We train the model and then print the parameters value after the model has been trained. Again, in this case, we can see that the model is actually learning from the training data. Final weight initialization technique that we'll use is He initialization. This initialization technique is used for ReLU and its variants like leaky ReLU. The weights are initialized by drawing from a distribution with a mean of 0 and variance of 2 by number of input units in your neural network. Similar to how we did this for Xavier initialization, we use He initialization to define the weights for both our linear layers. We continue to use normal distribution for initializing the biases for our neural network. We create a model object, print the value of parameters before model training, train the model, and then print the parameters after the model is completely trained. So these are few weight initialization techniques in PyTorch. If you found this helpful, please like the video and subscribe to my channel. If you have any questions, put them in the comment section. Thank you for watching the video.